Welcome to Geology Lecture. This is Professor Diana L. Pomeroy, and this week we'll be learning about California's tectonic history. This slide shows a geologic map of California. Geologic maps have an overlay of distinct rock units or formations that are situated above a topographic map. Formations, as discussed in the Geologic Time lecture, represent different types of rocks such as igneous, sedimentary, and metamorphic rocks, although most of the time when we talk about formations, we're referencing sedimentary rocks. And they also represent distinct periods or epochs of geologic time in a region. Each period of time on a geologic map is represented by a different color, and each type of rock has a symbol that's drawn on that geologic map. So on this map of California, we have multiple colors that are representing distinct formations and distinct units of time. So we notice that there's a lot of red here and a lot of yellow and green. These correspond to distinct moments in California's geologic history, which I'll be discussing later on. The geologic region of California is incredibly complicated. We have evidence of divergent, convergent, and transform boundaries, in addition to the presence of several mountain ranges in our state. Recall that divergent plate boundaries are where tectonic plates move apart from one another. This creates a ridge in the center, and tensional forces will be exerted on the landscape. Convergent plate boundaries are where tectonic plates collide. This creates mountain ranges. It can also create subduction zones, typically at the boundary point between oceanic plate and continental plate, and trenches as well. And then we also have island arcs, typically at the boundary point between oceanic crust and oceanic crust together. Convergence creates compressional forces on the landscape. This can result in folds, and it also can result in a phenomenon that we call tectonic uplift. So usually whenever we have compressional force, sections of sediment or other rocks are being pushed up to the surface in this process. Transform plate boundaries are where tectonic plates move past one another along a fault zone, and that's what generates a specific type of force known as shear force. Transform boundaries are often associated with mid-ocean ridges or rift zones. They offset sections of a ridge to the right or to the left. Tectonic activity, such as mountain building events, otherwise known as orogenies, can be traced in the rock and fossil record. Now, this rock and fossil record, just as anywhere around the world, is not complete. It's an incomplete fossil record. There's an incomplete rock record. Recall that this is due to erosion. Those erosional events produce what are known as unconformities, which we've discussed in the Geologic Time lecture. In addition to all of this, because of the presence of all the tectonic boundaries in California at some point throughout its geologic history, our geology is incredibly complex. There are several books that are written about the geologic history of Southern California, and they're still being refined today. So a lot of the concepts that I'm going to be covering are just general concepts of California's history. If you would like to know more about the concepts I'm presenting, feel free to go ahead and check out some books on the geologic history of Southern California. Areas with distinctive geology are called geomorphic provinces. The formations preserved in each province give us clues as to, in this case, how California was developed millions of years ago. There are 11 geomorphic provinces in California, as shown on the diagram in this slide. We will focus on the following provinces during our review of the geologic history of California: the Mojave Desert, featured here in tan; the Sierra Nevadas, featured here in like a peach; the Basin and Range, featured in pink; the Klamath Mountains, featured in like a neon pink or baby pink; and the Transverse Ranges, which are featured in light blue. So those are the major geomorphic provinces in California that we're going to focus on for this lecture. Before we do our overview of about 600 million years or so of geologic history in California, I want you to understand that the California that we know today is very different from what it was millions of years ago. For much of its geologic history, California was submerged. It was completely underwater. And so this vista that we have today, in this case of downtown Los Angeles, nestled within the hills, in the transverse ranges, parts of the Santa Monica Mountains, parts of the San Gabriels, that particular vista is relatively recent in terms of geologic time. The vast majority of California's geologic history, it has been completely submerged and underwater. This slide has an illustration by Ray Troll. He's a paleo artist that's famous for the book Cruising the Fossil Freeway. So if you'd like to, again, check it out in your spare time, you can. So on this illustration, we have a colorful outcrop of strata. Recall that strata are usually layers of rock, possibly formations, that are stacked one atop the other. And an outcrop is a cliff that we can observe, in nature. So usually an uplifted section of layers of sediment typically. So in this case, we not only have the strata on the left side with some representative fossils and major boundary points between each of the eras of time, but on the right, those layers have actually been divided into our geologic time scale. So the geologic time scale here is divided into the Archean, the Proterozoic sections of time. Now, I didn't get into those. I will be posting some lectures later on YouTube that will go more in depth with certain aspects of geologic history. But instead, we're just going to focus on the three main eras of time, which in order from oldest to youngest are Paleozoic, Mesozoic, and Cenozoic. There's also some periods within each of these eras that I will be mentioning throughout the lecture. So let's start our tour of California with the first era of time, which is the Paleozoic era. During the beginning of the Paleozoic era, California was covered in shallow seas. The shoreline of the North American plate was a passive continental margin. Lime mud and sand gradually collected and built up along the gently sloping coast. The coastline, the actual boundary point between the shallow sea and the landscape, was once where Arizona and Utah are today, which will be shown on the next slide. So this slide shows a map of Western North America with the states labeled, and this time frame is the Cambrian period. Note that California is it's completely submerged. So California is situated on, again, this shallow sloping continental shelf. It's leaning out into the deeper parts of the ocean, and so that's where we are approximately 500 million years ago. This slide shows what the world looked like during the Precambrian and through much of the early Paleozoic. North America is in the center of this globe. So this is what the Earth's surface looked like. The earliest Paleozoic rocks in Southern California are preserved in the Mojave Desert. They date back to about 600 million years maximum in some areas. So these images are taken from Google Earth, and here are some sections of the Mojave Desert. So the Mojave actually contains evidence of some of the oldest rocks here in California. From the middle to the end of the Paleozoic, there was an orogeny event that took place. So recall that orogeny events have to do with mountain building, typically. Now, the event that happened here is known as the Antler orogeny, and there's a lot of debate as to whether this represents a true orogeny event, but I'm going to describe it as such. The Antler orogeny is due to the gradual buildup of sediment on the ancient coast, as you can see in these illustrations from Geology Cafe. So we've got this phenomenon known as accretion. To accrete means to add. So sections of sediment have been added to this region over time. In addition, there is a process of subduction that is going on between the plates as they collide with one another. So what happened during the time frame of the Antler orogeny is that we've got these sediments that are gradually building up along the west coast of North America, and a volcanic arc begins to be pulled into that coastline, and it essentially gets accreted to that coast. So the Farallon plate begins to converge with Western North America during the end of the Paleozoic. And that subduction continues for hundreds of millions of years. So this accretionary event, what happened was sedimentary rocks, igneous rocks, they begin to be added slowly to the west coast of North America and expanded it throughout the Paleozoic, and especially towards the end. So this slide shows the stages of the Antler orogeny in more detail. This image comes from Ron Blakey, who also did the paleogeographic maps that I've been showing you throughout this lecture. So again, during the Devonian, Mississippian, and Pennsylvanian, these are the phases of the Antler orogeny, and you can see that not only is California involved here, but so too are the states of Nevada and Utah. And you'll see how this process of subduction and accretion is what essentially created this mishmash of all kinds of geology here very early on. So this whole process, again, took hundreds of millions of years. So these slides show maps of Western North America, and the states are again labeled here for you. And the first image is from the middle Mississippian period from the Paleozoic era. You'll note that California, just as before, is still underwater. So California is completely underwater. There's a few island arcs that are beginning to converge with the mainland. In the Mississippian, note that we had much higher sea level at this point, so the entire continent has been flooded. And as we move forward in time to the Permian, so to the very end of the Paleozoic, here's what happened. Here's California forming. Again, that convergence point, the west coast is beginning to build. Now, what's notable about the Permian is that not only is the Antler orogeny in full swing at this point, but the entire world, all of the continents, have merged into a single land mass. And that is a landmass that we've mentioned before. And that landmass is Pangaea. So on this slide, it shows what the world looked like during the end of the Paleozoic era and the end of the Permian period. Pangaea is formed. So it's a supercontinent. So all the continents have been merged into this single land mass. Again, as with the previous globe, North America on the left globe is in the center, okay, of this illustration. And so you'll note that on the west coast of North America, again, it's completely submerged. There's some island arcs that continue to accrete, and this process of subduction of the Farallon plate, which is a portion of the Pacific Ocean basin, that subduction process with the west coast of North America will continue throughout the Mesozoic. Now, Pangaea, okay, as we know, right, evidence for this was provided to us by Alfred Wegener in the 19-teens, right, when the hypothesis of continental drift was first proposed as part of the theory of plate tectonics today. So this concept, right, that Pangaea existed is based on the evidence that he provided from the fossils that existed during this time frame. Now keep in mind that at the end of the Permian, right, not only is Pangaea forming, and so the land surface is undergoing a lot of pressure and change, but also recognize that at this time we also had a major mass extinction. So here we've got some mid to late Paleozoic rocks that are present in California, and they're preserved in the north. They're preserved in the Klamath Mountains in the north. And so here's a photo again from Google Earth, and you can see the environment there and those high peaks. The sediments there are from the Paleozoic time. So we're talking more probably in the order of 300, maybe 250 million years ago, that time frame here. The end of the Paleozoic, as I mentioned to you before, had a major mass extinction event that wiped out about 90% on average of all known life on Earth. So Pangaea throughout the end of the Paleozoic, all throughout the Mesozoic, began to split apart. So again, continental drifts began to happen throughout the Mesozoic. So let's talk about that next era of time. So now we're out of the Paleozoic mass extinction event. Now we get into the Mesozoic. During the Mesozoic era, subduction would continue. And again, that's between the Farallon plate and the North American plate. So that subduction process, again, the Farallon plate is connected to the Pacific Ocean basin. So the Pacific Ocean, essentially that ridge that sat in the center of the Pacific, began to move from the center point at the beginning of the Mesozoic all the way through till the end. This process of subduction would continue. So the Farallon plate would just continue to subduct, continue to get pulled underneath the North American plate, and as a result of this process of subduction, what were generated were these massive pools of magma. These massive pools of magma would then feed into giant ancient volcanoes. And these giant volcanoes, their range is known as the Cordilleran, so the Cordilleran Range and Orogeny began during this time. Now, if you look at the diagram here from Geology Cafe on the right, towards the end of the Mesozoic, the Western Interior Seaway began to fill the center of North America at this time as well. So again, this pool of magma would eventually solidify into a granitic and dioritic basalt, an igneous structure. So this huge plutonic igneous structure that we see today and remnants of the Sierra Nevadas actually began to form during the Mesozoic era in this process of subduction. So this slide shows the process of subduction between the Farallon plate and the North American plate in a little bit more detail. Note that the Sierra Nevadas again were once immense volcanoes with felsic lavas that would later then solidify into those intrusive igneous rocks, granite and diorite. Note that the coastal ranges, sections of the coastal ranges are present in Southern California. So local mountains like the Santa Ana Mountains, Anaheim Hills, the basis, the bedrock of those mountains was being developed during that time. And those sediments are mostly from ancient marine sedimentary environments. So a lot of sands and conglomerates, sandstone and conglomerate type sedimentary rocks were being pushed up and then accreted along the shoreline. And that accretionary wedge would then result in erosion, and that erosion from those ancient mountains would then spill out into a low-lying area that we call the Great Valley. So the Great Valley would form between the coastal ranges and the Sierra Nevadas that other geomorphic province would then develop. So that process of subduction, as the sediments from the seafloor began to be pulled into the mantle rock, what had happened is sections of the seafloor, that basaltic rock, also began to be compressed and superheated, and it generated the foliated metamorphic rock serpentine. And serpentine is our state rock here in California, and it was first formed during the Mesozoic era. It's evidence of this process of subduction that went on for a very long time. So these slides show, again, maps of Western North America, and we've got all three periods of the Mesozoic era represented here. So this is the Triassic period, about 215 million years ago. Here is California, again, completely submerged underwater. It's off, again, the west coast of North America. We're past the continental shelf still, so we're not really part of the continent yet, technically, during this time. And we won't be for a long time. You'll note that throughout the Mesozoic, there's a lot of changes with sea level, and you'll see that in the next slide. So here in the Jurassic, about 150 million years ago, continued accretion because of subduction, coast ranges beginning to form, the Sierra Nevadas beginning to form, that constant volcanism happening, still ongoing. So again, Jurassic period, this is what California looked like. And then finally, in the Cretaceous, the Western Interior Seaway in the center of this map is beginning to form and flow, and California, once again, is still not there. It's still part of the continental shelf. This slide shows what the world looked like at the very end of the Mesozoic era, approximately 66 million years ago. The continents have all drifted into their relatively current position. So this is about where the continents were 66 million years ago. They look recognizable now, right? They've drifted completely apart from where they were at the beginning of the Mesozoic. Note that here in this illustration, this map, we've got a little bit more of California forming, but it's still not quite there yet. Okay, notice also there's been a sea level change, right? The Western Interior Seaway has evaporated, has receded and dried up. There's huge changes with this climatically, and as we know, at the very end of the Cretaceous, 66 million years ago, there was an asteroid impact that hit the Yucatan Peninsula, and that led to the extinction of the non-avian dinosaurs, among other creatures at the end of this time frame. The cores of those ancient Cordian volcanoes, they do still surround us today, especially in the Sierra Nevadas. Here, what's pictured here is Yosemite. Okay, so here's Yosemite National Park, which again we've learned about in the glaciers lecture. So here we have those ancient granite and diorite cliffs that were once part of a massive volcanic pool of part of a volcanic system. They're part of a pool of magma that have been uplifted and eroded by glaciation. So their presence, the presence of these massive granite batholiths throughout our state, this indicates that much of the Mesozoic era in California is going to be missing. It's going to be in terms of sediments and fossils. A lot of that time frame, except for some of the fossils that we find in the coast ranges from this time, like a lot of sea creatures and things, that's typically what we find. So a lot of the terrestrial life from this time frame was not preserved, if anything was here at all, really. Very few creatures lived in California during the Mesozoic. We don't really have a whole lot of evidence of this because of that phenomenon of subduction. It completely destroyed whatever sediments were there, with the exception again of the coast ranges that were accreted sections of marine sediment. So very few terrestrial fossils are preserved from this time in California. And that's part of the reason why we don't really have a whole lot of dinosaurs here in California. This is not the state to excavate dinosaurs in. It is here. So the end of the Mesozoic, again, as I mentioned to you before, we had a major mass extinction, the asteroid impact of the Yucatan Peninsula, changes to climate, also associated with volcanic eruptions and the Deccan Traps in India. These things taken together wiped out about 75% on average of all known life on Earth, including the non-avian dinosaurs, flying reptiles like the pterosaur, like we see here in this illustration, and then we've got swimming reptiles, marine reptiles as well. All of those creatures are now extinct. Mammals and birds and other reptiles and other creatures that made it past that boundary point, they filled the niches or ecological roles that were left behind by the dinosaurs and their relatives the non-avian dinosaurs is what I mean by that, during the Cenozoic era of time. So now let's move in to the Cenozoic era, our era of time, the age of mammals. The Cenozoic era was the most geologically active time in California. This slide shows diagrams of the ongoing subduction of the Farallon Plate, so it was still going on during the Cenozoic. It finally ended about 20 million years ago. So during the Miocene epoch of the Cenozoic era is when that process of subduction finally ended, and a lot of things began to happen to the North American continent during that time. So between 20 million years ago to the present day, we've had a lot of geologic change in North America, not just here in California. So California as a state really didn't begin to exist until the late Cenozoic. The rest of this time, it has been part of the west coast of North America in terms of like continental shelf material, in terms of part of a subduction zone region. It really wasn't developed as its own landmass until a distinct portion of the North American continent until the end of the Cenozoic era of time. So during the early Cenozoic, we had that process of subduction, and then in the end of the Cenozoic is when we start developing our San Andreas fault system, fault zone. Multiple faults are forming here, and crustal extension of the mountains to the east, the Basin and Range region, Rocky Mountains further east. Okay, all of this began to happen during this time. So from around 40 million to 20 million years ago, so that means that we're starting in the Eocene and moving on into the Miocene epoch. Subduction of the Farallon Plate continued. Now recall that in all this time, right, in all these hundreds of millions of years throughout the Mesozoic, the mid-ocean ridge that used to sit in the center of the Pacific Ocean began to be pulled eastward. As it began to be pulled eastward, that mid-ocean ridge, which the eastern boundary of that ridge being the Farallon Plate, continued to subduct beneath the North American plate up until 20 million years ago. So on these diagrams by Stephen Marshak, you can see that phenomenon happening. We've got the mid-ocean ridge being subducted, pulled slowly underneath the North American continent, and when that process happened to stop, there was a transform boundary, a transform fault that had been caught up in that process. It was then twisted and rotated, and that became our transform plate boundary today. 20 million years ago, or roughly 20 to 30 million years ago technically, that's when the San Andreas Fault system began to form, was during this time. Now, in addition to this, because we've moved this divergent boundary from the center of the Pacific Ocean to the center of North America, well, Midwest and North America, because we've moved it over, what's happened is that the divergence that's going on, that tensional force, is going to affect and essentially lengthen and extend sections of the North American plate. And so that's going to generate a region that we call the Basin and Range. So that province began to form during this time as well. So thus far, we've encountered the Sierra Nevadas, we've encountered Klamath Mountains, the Basin and Range. In addition to this, the San Andreas, as it developed, also moved around mountains, and that's what generated our transverse ranges that we have that essentially mark the boundary points of sections of LA County, are those ranges. So during the late Cenozoic and until the present day, because this is an ongoing process, right? Tectonic activity does not stop. So we right now are on the San Andreas Fault, and technically in Southern California, recall that we are actually on the Pacific Plate. So the Farallon Plate is no more. It was subducted beneath North America starting around 20 million years ago, and after that process ended, the San Andreas Fault Zone began to form. And this transform boundary is what's moving sections of the Pacific Plate against the North American Plate. So this illustration shows evidence of the San Andreas Fault, transform boundary. To the north, we've got some subduction going on, generating the Cascades in the Pacific Northwest. To the south, we have also subduction, but then we also have some divergence with Baja California. That peninsula was developed through the process of divergence, because again, that divergent boundary that used to be in the middle of the Pacific Ocean is now underneath North America. And all of these processes together are kind of pushing and pulling mountains around. It's moving and rotating sections into place. And it's also moving around and making volcanic activity happen in different parts of the state. So in Northern California, remember, we've got active volcanoes. In Eastern California, we have Mammoth Mountain. So we have various volcanic activity that's happening. And a lot of that is due to this recent tectonic motion, recent meaning roughly 20 million years to the present. We've got the San Andreas forming. So without the San Andreas fault system, moving sections of our state around, moving our mountains into place, even with that process of tectonic uplift in sections of it, our state would not exist without the San Andreas. So here's another illustration, again modified from Stephen Marshak's illustration. These images come from the National Park Service. So we've got the San Andreas fault system, and again, it's a very gradual process over 30 million years, and again, the San Andreas is still active. We have a lot of active faults here in California, and that shear stress is what's kind of moved around sections of mountains and valleys, and sections of that ancient granite from the Mesozoic have been shifted and moved from this fault as well. And each of the major national parks that we have here in California were put in place during the Mesozoic and Cenozoic time frames. So as you can see on this illustration, places like Death Valley, Mojave, those are older, right? Mojave is the Paleozoic, parts of Death Valley also, and then we get into the Mesozoic with the Sierras and Yosemite and the Great Valley as well, and then the San Andreas Fault, once it rotates into place, the transverse ranges will be rotated as well and developed, along with the Channel Islands, the sections of the Santa Monica Mountains, all of our major beaches here in Southern California. They were rotated into place due to that motion of the San Andreas over 30 million years of time. And we have evidence of this from paleomagnetism. So there are scientists that study the changes to the magnetic field. Position of those changes can indicate changes to the rotation of certain tectonic blocks or rocks on the Earth's surface. And all of this can indicate extreme change. So our landscape is incredibly varied because of these processes, because of these tectonic forces that are continuously shaping and moving sections of rock around, always shaping our coastline. So these slides, just as before, will show you some more maps. Here we've got different epochs in the Tertiary and Quaternary periods within the Cenozoic era of time. So we've got the Eocene here, about 50 million years ago. The Eocene epoch, we've got California, which again, at this point, 50 million years ago, it's still undergoing that process of subduction. And you'll see that there's going to be some slight changes to the east of California here as we progress through the Cenozoic. So here's the Eocene-Oligocene boundary, about 35 million years ago. Again, subduction is still ongoing. And it's really in the Miocene when that process of subduction will end, and you can start to see sections of the San Andreas off the coast of California. In fact, you can see the beginnings of what would eventually become the San Francisco Bay Area, and sections of that will be moved along that fault system. Sections of uplift will occur here, and sea level will drop from the Miocene moving forward, especially during the past 2 million years during the Pleistocene epoch, during the last ice age, last glacial maximum, right? So all of those phenomena together will eventually shape California into what it is today. So that process of subduction has ended at this point, and note what happens here with the basin and range on the next slide. So the basin and range has completely expanded that coast throughout the Miocene, slowly expanding to the east of California, slowly pushing the coastline westward, and sections of the Channel Islands begin to be formed during this time, during the latter part of the Miocene, and getting into the later epochs of time with this last image. So this last image shows California in the present day. Now, California in the present day, again, everything was rotated into place and moved around due to the San Andreas starting really around 30 million years ago, but around for the past 2 million years, okay, with sea level drop and tectonic uplift, all of this surface has completed. So as far as fossils and as far as our geology here too, so a lot of our sediments here that we observe in the hills around us and that we excavate, a lot of those sediments contain fossils that come from the epochs of the Cenozoic, in particular from the latter epochs like the Pleistocene and the Holocene. So this slide shows some examples of mammals from the Pleistocene that lived in Southern California. And all of these specimens are on display at an interpretive center in Buena Park, California. It's actually in a regional park. It's in Ralph B. Clark Regional Park in Buena Park. So for those of you that are, say, visiting, Southern California or that live here, we do have smaller museums that you can visit that house these types of specimens. So we've got on this slide various organisms that lived here in Southern California just a few thousand years ago. We have creatures like tapirs, which now are common in South America and parts of Central America. We had horses here at one time, saber-toothed cats, giant ground sloths that grazed and moved across the landscape, and also, of course, dolphins, right? Dolphins not only exist today, but they also existed here along our ancient coast a few thousand years ago to a few million years ago, give or take. So this slide has a mural by Mark Hallett of the creatures from the previous slide, in addition to some more. So in the center here, we've got a llama. So we had llamas here. And in fact, there was a migration event between the Americas once the Panama Canal had risen from the sea. It allowed for various creatures to migrate between the Americas. And that's why in California we have evidence of those types of creatures here. Now, unfortunately, a lot of them went extinct. However, there's a few that still remain here, like the opossum. So the opossums that you might see in your backyard, they actually originate from South America. They migrated here thousands of years ago. So we've got llamas here. We've got Canada geese, which are still here, flying overhead. We've got some mastodons in the background. We have an ancient horse. We have some tapirs as well. All of these creatures living in this savanna, chaparral type environment that we've had here in Southern California naturally for thousands, again, to about, a couple million years or so. So the Miocene, Pliocene, Pleistocene, and Holocene, again, the latter two being more common here, we have a lot of fossils from those formations. And again, these images come from the Ralph B. Clark Regional Park Interpretive Center. And we've got some formations that are right outside our backyard. They're in the La Habra Hills. There's actually formations that have been uplifted, and you can actually excavate some of those areas. I don't recommend that you do that, by the way, without a permit, okay? But those areas just here. In addition, whenever we build, let's say, subways here in Los Angeles, like I mentioned to you in the lecture with glaciers and ice ages, right? Anytime that we do those things, we find all kinds of evidence of ancient life here from thousands of years ago. And so all of these things are right here. Resources are right here in California. So again, while we may not have creatures as awesome as dinosaurs in Southern California, we do have quite a wealth of fossils and evidence of life from, the past 60 million years going forward, with evidence of changes to our landscape, changes to life here. And again, we've had a very unique geologic history. Many of the concepts that I've covered from previous lectures will help us understand how this wonderful state came to be. So I hope that you enjoyed this lecture, and I'd like to thank you for watching. Hope to catch you in the next one.